Hi guys, this is Mrs. Gastler, and in this video we're going to talk about angular momentum, which is a lot like regular momentum, but it's angular, okay? So to begin with, we're going to talk about just a single particle that's going in a circle, and pretend that's a perfect circle. Oh yeah, it's a great circle. And it's going around this point somewhere in space, and here's our actual particle, there's our particle, okay? Maybe it's a ball, who knows? But it's going this way and it has this velocity v, okay? And it's at some radius r from the middle. And we're going to pretend that that's exactly perpendicular right there because it's moving in a circle. And so when it's traveling in a circular path, that velocity is perpendicular to the circular path, which again, that's a perfect circle. Remember that, okay? Now, in linear motion, we would talk about momentum p, and we would find that by doing mass times velocity v, which we could still do. This object does have mass, okay? And it would have the units of kilograms times meters per second. But now we are dealing with angular momentum. And so our angular momentum, we actually call it angular momentum, because I haven't written that enough times yet, is the capital L, and it's also a vector, so it has that sign on it, okay? And we're just going to do what we've done so far with a bunch of our linear and angular quantities. What has been our angular equivalent of mass? Angular equivalent of mass has been that rotational inertia. Mass is a measure of inertia. That tells us how much it doesn't want to change what it's doing. Linearly, rotational inertia tells us how much it doesn't want to change its rotating. So we're going to use that angular equivalent there. And then instead of linear velocity, we'll use angular velocity. And so that is our angular momentum. And our units would come from that. The units of rotational inertia is kilogram meters squared. And then our angular momentum is radians per second, but the radians just kind of fade into the background here, and then we just use per second like that, okay? And so they have similar units, but they're not quite the same, and that's because of that whole, it's moving in a circle. But if you remember things like V equals R omega, and theta equals R S, and what is it, alpha equals R, A, oh, I got that backwards. S equals R theta, and A equals R alpha. So it's always the linear equals R the angular, okay? So it's doing the same thing here. Actually it's not. We've got an R times the original, so we've got an extra meter in here. We'll get this into this format here in just a second. Okay, so another way that we define angular momentum is in terms of the vectors, and that's actually where this comes from, but we'll start there in a second. So let's take that I and that omega, and let's go the other way. Okay, so I is for a particle that's going in a circle, it's just mr squared, okay, and omega, if we solve this for omega, is v over r, okay? And if I do a little bit of rearranging, you'll see one of those r's cancels out. So I have m and r and then v. And maybe you've seen m times v before, right? So look at that. I just got this into L equals r times the momentum, okay? Now, when we're dealing with vectors, r is actually a vector, and so to do this kind of math here for you AP Physics C mechanics people, that's actually a cross product. Let me draw an arrow there instead of an equal sign. L equals r cross P. And we did a cross product with torque, so it's the same kind of thing there that we're going to be doing, that r cross P. For you AP Physics 1 students, that cross product, well, this works for everybody, that cross product is r times p, or rmv, times the sign of phi. And where phi is, I'm going to kind of redraw that picture. So we've got our r up to our particle, and it's going off this way with our velocity, here's r. So that phi would be measured right here, okay? So if our r was off this way and our v was like this right here would be our phi, r, v, okay, like that. Here's our particle. So that would be our angular momentum measured that way. So that's where that phi is, okay? And so that's the couple of ways that we measure angular momentum there. Something to note, angular momentum, like linear momentum, a total momentum would be the addition of all of the pieces. Whoops, that should be an equal sign, 1 plus, 2 plus, however many you have. And they are vectors, so they have some directional quality to them. The directional quality of the angular momentum is going to be kind of like torque. It'll be like clockwise and counterclockwise. Okay, so if they're in opposite directions, you would subtract, and in the same direction, you would counter. I forgot the clock in there. If they're in the same direction, you would add clockwise, like that. Okay. And that has some important, what do you call it, applications. Later we'll talk about conservation of momentum and with some collisions and some interesting things like that. Okay, thanks for watching.